And so when we bring it in on Monday, where do we put it, or?
Where do you put it? You just bring it to the Natural Science Division office, which is over here in the corner, and then they'll put it in my mailbox. Just say this is for.
And they close at 4:30, right?
That's something you want to verify. 4:30 or 5.
Is it okay if we turn in lab 2 sometime after our final? Would that still be okay? Or
You could, although there could be a late penalty. The labs, the homework you could turn in up until Monday as well. But the labs, there might be a late penalty.
So the last day to turn in anything is Monday?
The last day to turn in anything is Monday. So turn in all your late work on Monday. Got that.
like your final is my last final, so after that I have all the time in the world to do the lab and the paper and everything. So
why don't you take a look at the calculations for experiment 2? I think they're incredibly easy to be, just go back. If somebody wrote down the equations, see what the equations they wrote down are. But the actual calculations aren't going to take you very long. Plus, it's good to review that material for the final. The calorimetry stuff. I don't know how many people got hurt on that thermo test, but if they did the calculations from the lab, it wouldn't have been that bad, I would imagine. And so it doesn't hurt to review. Use that as a review for the final, for the thermo. But take a look at the calculations, and you'll see, actually, who completed it? Experiment 2. Anybody complete that? How long did you spend with the calculations? It was quick, right?
The graphs took a long time.
The graphs took the longest time, but we did those in the computer lab, right? And so, there are people with zero Excel experience who managed to get through those. So I would use that time to use that. Those calculations and experiment them 2 are good for calorimetry and good for calorimetry review. And I would recommend looking at those. Are we on? Although there are 2 chapters left. Basically, it's not that much stuff really, because it's just liquids, solids, and solutions. And so how much can you say about liquid, solids, and solutions? And so let's take a look at we're going to spend some time, actually quite a bit of time, talking about intermolecular forces. The intermolecular forces, you guys should already know from Chem 4 or Intro Chem what they are, right? You have the London or the dispersion or what they call instantaneous induced dipole. All those are the same thing. You have the dipole interaction, or you have the hydrogen bonding interaction. But you can have some composite intermolecular forces as well. We'll talk about those. The van der Waals force is the name given to these weak attractive forces. Weak because they aren't as strong as a bond, but still they can be fairly significant. And so the first intermolecular force, or the first van der Waals force we're going to look at. And van der Waals, that name should sound familiar. Do you guys remember van der Waals? The van der Waals equation for real gas. Van der Waals was investigating, what impact intermolecular forces have on gas pressure, volume. And he compensated for intermolecular forces in his equation by the variable A. You guys remember the A? A increase with the strength of the intermolecular forces. And so let's take a look at the intermolecular forces that we have. And A here, this could be like a helium atom. In other words, helium atom would be something that's non-polar. If you look at this, B, this is polar. Polar because the electron cloud has been distorted. You can see over here on the left, built up negative charge density, on the right, some positive charge density. And so what happens in dispersion London instantaneous induced dipole is this. time average, it looks like this. But in one instant of time, if you freeze the electrons, maybe both electrons are on the left side. If both electrons are on the left side of this atom over here, then in an instant of time, we have a dipole. And this dipole doesn't live for very long. Rapidly, the electrons move about, and this dipole disappears. But with this instantaneous dipole, that's what we call it, it can induce a dipole in an adjacent atom. So here we set up an instantaneous dipole, which induces a dipole here. So we would have had a green atom here. And because of the positive charge density here, the electrons of the green atom are pulled over here, and that causes this. The color coding here is based on electrostatic potential maps, with red being negative charge density, blue being positive charge density, and green just being even distribution. And so this attraction only lives for one instant, but what happens is it continually forms, continually breaks, and we end up with a net attraction. This net attraction is going to be related to something called the polarizability. What the polarizability is how easy is it to distort this electron cloud here. And when you look at the electron cloud, it's hard to say how easy it is to distort, but we can make a comparison between something like helium and xenon. Helium is not very polarizable, because helium only has 2 protons and 2 electrons here. And so the electron cloud can be polarized in an instant. That is, both electrons move over here, and then we set up an instantaneous dipole. So both electrons here, therefore this end becomes delta negative, this end becomes delta positive, and this can induce a dipole in an adjacent helium, which will cause a fleeting attraction. But if we have something like xenon, xenon is very polarizable because xenon has 54 protons and 54 electrons. Let's put that here. This is much bigger. So if we're looking at 54 electrons, if we have a lot of electrons over here, let's say 30 electrons over here, then we're going to set up a huge instantaneous dipole as the electrons migrate over here in one instant of time. And then it disappears. But with this instantaneous dipole, that's going to induce a big dipole in an adjacent xenon and cause it a pretty strong dispersion force attraction here. And so we could show this attraction by having some dots here. And so this is the dispersion or the London force. I just call it dispersion. Easy. And so we move some electron density here, and that's going to cause the electrons to move here, induce it. In the next instant of time, it disappears, but the new ones are constantly forming, so net overall, we see an attraction. One of the ways you can determine the strength of the intermolecular force is by measuring its boiling point. And so here, the boiling point of helium is very low. Boiling point is only 4 Kelvin, extremely low. There are 2 ways to think about this boiling point. One way is to think about this. The attractions are so weak, right? You have to cool the atoms down to 4 Kelvin to get them to stick together. Like if you're at 5 Kelvin, it's too much kinetic energy, the atoms break apart and goes back to gas. And so that's one way. The other way is if we think we have helium liquid. If we have helium liquid, the atoms are being held together. They're stuck together in the liquid state. And so if we have helium liquid, all we have to do is heat that or warm that to 4 Kelvin. Once we're at 4 Kelvin, the atoms break apart, the whole thing vaporizes. All right, the boiling point for xenon is going to be much, much greater than 4 Kelvin. The boiling point for xenon. And that's because the dispersion attractions here are much stronger. And so polarizability is going to be related to how many electrons. The more electrons you have, the more polarizable the species is. Well, a lot of people don't want to count the electrons, because it's kind of a hassle. It's not difficult, it's just a hassle. Whereas, most people already know the molar mass. And so they use the molar mass as a indicator of how many electrons there are. The higher the molar mass, the more electrons you expect. They don't use the molar mass as an indicator of how heavy the molecule is, because these molecules are extremely light. It's an AMU. And so even though carbon tetrachloride looks heavy, an individual molecule of carbon tetrachloride is not heavy. Gravity doesn't hold carbon tetrachloride down. Carbon tetrachloride is held down by intermolecular attractions or intermolecular forces. But let's take a look at these. So here, the number of electrons is increasing. As the number of electrons increases, the polarizability increases. As the polarizability increases, then the degree, the magnitude of these instantaneous dipoles that can form increases, and therefore its boiling point will increase as well. The interesting thing about all these molecules, all these are non-polar, so the only thing holding these together are dispersion. And dispersion can be actually quite strong because carbon tetrachloride is a liquid, and this liquid boils above room temperature. What is room temperature, about 298?
Yeah.
And so this carbon tetrachloride is boiling around, 50-something degrees C. Just held together by dispersion. Well, the dispersion for carbon tetrachloride would be strong because chlorine has a lot of electrons. A lot of electrons means more polarizable. And so the trend is simple. The trend is the bigger the molecule, the stronger the dispersion forces. In fact, the dispersion forces can be so strong that we don't get a liquid, we actually get a solid. An example of a solid would be like wax. Wax is a hydrocarbon, except it's not short chain, Short chain would be like C3. It would be a long chain, like 20 carbon atoms. You have 20 carbon atoms in that chain, sp3 zigzag chain. That's going to be solid. And it's a solid because of the dispersion forces. So wax, asphalt that they use to make the streets is made out of what? Crude oil, tar, basically hydrocarbons. And these are very big molecules. So these big molecules have strong dispersion forces which hold them together. Okay, so the number of electrons, that is the molar mass, makes a difference. These two have identical molar masses. These two are called isomers. This is one isomer. This carbon is surrounded by what we call 4 methyl groups, neopentane. This carbon is tetrahedral, so this whole thing has a spherical symmetry to it. Whereas this is just a chain, zigzag chain of sp3 carbons here. If you look at the boiling points, neopentane is 9.5, pentane is 36.1, same number of electrons. The difference is in the surface area. When you have a spherical shape like this, we have minimal surface area. Whereas if we have a long, straight chain, not exactly straight, but a long chain of carbons, the surface area increases, and it turns out the dispersion forces are going to be, be dependent on surface contact, surface area as well. So the greater the surface area, the stronger the dispersion forces. And so there are two things with dispersion. One, the number of electrons, i.e. its molar mass, and two, its surface area. Both increasing surface area and increasing number of electrons means stronger dispersion forces. Pentane's a liquid at room temperature. Its boiling point is above 25 degrees C. Neopentane is a gas at room temperature, so it's much weaker intermolecular attraction.
Professor, you said the number of electron increases, which makes the bond stronger, but
the dispersion force is stronger. As the number of electrons increase, then the distortions to the cloud can become much more significant. Here, the maximum number of electrons that can move to the left is 2. So if all 2 electrons move over here, then we're going to set up a dipole. Delta minus, delta plus. Here, the maximum number of electrons that can move to the left of this atom are 54. So if all 54 move over to the left, then you're going to set up a much bigger dipole moment than you could with helium. And therefore, xenon is what we call much more polarizable. The distortions of the electron cloud can be huge.
Doesn't the density matter in this case? The charge density.
The charge density, yes, that matters too.
The
You're right.
is much bigger, so
Yeah,
why is it stronger?
xenon's much bigger. You're right. Xenon's much, much bigger, and so those would be competing factors. Yeah. Because here the heliums can get much closer, right, than over here. But in the long view of this, being able to distort this electron cloud this much results in huge delta pluses and delta minuses.
How does it affect BP?
How does it affect the BP? The BP, well, the stronger the intermolecular or interatomic attraction, the more difficult it is to break apart. And the more difficult it is to break these apart, the more kinetic energy you need, and therefore the higher the temperature. And so the stronger the IMF, the higher the BP. BP is just a convenient measure. There are other measures as well. I mean, we could use things like vapor pressure, viscosity, etc., which we'll talk about. All right, those are instantaneous dipoles. The next thing we're going to look at are molecules which have a permanent dipole. These would be like this. Over time, the dipole averages to this. That would be a permanent dipole. Over time, you see this dipole? Over time, this dipole averages to this nonpolar atom with a symmetric distribution of electron density. And so here we have permanent dipole moments which will impact its boiling point. And so nitrogen doesn't have a permanent dipole moment. Nitrogen is nonpolar. Its molar mass is 28. Boiling point is 77 Kelvin. Oxygen is nonpolar. If you look at its molar mass is 32, which means it has more electrons and is more polarizable. And so going from 77 to 90 Kelvin for its boiling point. And so from N2 to O2, it's more polarizability, therefore stronger dispersion. NO is kind of intermediate between nitrogen and oxygen. If we look at NO, molar mass is 30, but its boiling point is the highest, 121. And its boiling point is the highest because not only do we have dispersion forces are present in all materials.
What does the capital B stand for?
This one?
Yeah.
This one is what we call the dipole moment. Yeah, in Dubai, but I didn't talk about it at all. Yeah. This is, they talk about this in gases too. But you don't have to worry about the Dubai. It's just, there's something called a Gouillet balance. I didn't even talk about that. I think I skipped that, right? The Gouillet balance. That could be Chem 1B also, chapter 21, I think. But you can actually measure the dipole moment by measuring its attraction to a magnetic field. And when you measure it, then this is the units they use for that measurement. And so this just shows that there's a permanent dipole on NO, as we'd expect. so NO, you know, we expect the oxygen to be negative, nitrogen to be positive, something like NO. NO should have, NO is kind of a weird species because it should have an odd number of electrons. So nitrogen ends up losing out here. It doesn't quite have an octet. And so here, this is what we call a permanent dipole. You can't get rid of it. It's always there. And so these permanent dipoles are going to attract other molecules, like another NO molecule. And when we look at boiling, boiling is breaking apart these two NO molecules from each other. You know, they're kind of stuck to each other because of the dipole. This dipole interaction here with the delta minus is attracted to the delta plus. The delta plus is attracted to the delta minus. So to separate this would require breaking this electrical interaction. It's a dipole. Things get quite complicated though, because, you know, dipole is one thing, but dispersion is always there. And so let's take a look at some theories here, like methane. Methane is nonpolar, and then silicon tetrahydride or silane is nonpolar. And so we expect the methane, fewer electrons, silicon tetrahydride, more electrons. We'd expect the boiling point to increase, and that's what we see, the boiling point increases. And the boiling point increases because we have more electrons. And more electrons is going to be given by its molecular mass here. So you can see the molecular mass increases. If we go from silane to germane, germanium tetrahydride here has more, you know. So we're going just down the family: carbon, silicon, germanium, tin. The carbon, silicon, germanium, tin. The polarizability increases because the number of electrons increases. All right, let's take a look here. Ignore the green line here. Let's ignore it. And so if we go from tin to antimony, tin tetrahydride to antimony tetrahydride, they both have the same number of electrons. They both have the same number of electrons, however, their boiling point's different. And the reason they're different is because of the structure. Tin tetrahydride is tetrahedral, nonpolar, whereas antimony trihydride is trigonal pyramidal, so it's polar. And then if we go to hydrogen telluride is polar bent. And so what we see here is this: tin to antimony to tellurium. Tin to antimony to tellurium, the electronegativity is increasing. As the electronegativity increases, the dipole moment increases. And so the most polar would be H2Te. And so what we can say is that, you know, as long as the dispersion forces will be roughly the same. As long as the dispersion is roughly the same, then the highest boiling point will be the one with the biggest permanent dipole. Same thing happens here: germanium, arsenic, selenium. You know, increasing polarity means increasing boiling point. Silane, phosphine, hydrogen sulfide, increasing polarity, increasing boiling point. That is, increasing dipole moment. Ammonia, HF, H2O we'll talk about in a minute. But this is the trend. Now what's difficult is comparing molecules. These have been normalized, so you see roughly the same dispersion, the only difference being the dipole. But what if we take something that has a big dipole, like HCl? HCl has a big dipole, is chlorine is much more electronegative than hydrogen. Whereas tin tetrahydride, this is a very small dipole. In fact, no dipole, because this is nonpolar. And so which one has a higher boiling point? The one with the bigger dipole or the one with no dipole? Permanent dipole. This only has instantaneous dipole. You'd expect the one with a big dipole to be more strongly attracted to one another, but it's not. In fact, tin tetrahydride has a higher boiling point than HCl. Why is that?
The surface area.
It's not necessarily, it is related to surface area, but this is primarily due to
Mass.
polarizability. And so the take-home message of this is that it's difficult to compare. You know, usually what happens is when you get to large size molecules, dispersion wins out. I mean, you've heard of hydrogen bonding, right? Hydrogen bonding are the strongest attraction, correct? The strongest attraction. So HF, normally what is HF at room temperature? Gas, liquid, or solid?
It's liquid.
HF is a gas at room temperature. If it's a gas at room temperature, how strong are those intermolecular attractions? Not very strong. Whereas, you know, some hydrocarbon, some big hydrocarbon, it's only dispersion forces, and yet that's a solid. And so what this is telling you is this: size wins out. You know, as the molecules get bigger and bigger, that's going to dominate things because the dispersion get increasingly strong. Does that make sense? So it's weird because HCl being the most polar with the biggest dipole is actually weaker than tin tetrahydride with no dipole. Okay, but there's 3 species with unusually large dipoles. The 3 species with unusually large dipoles are nitrogen bonded to hydrogen, fluorine bonded to hydrogen, and oxygen bonded to hydrogen. And so those are called H bonding interactions. But let's stop for a moment and just look at normal dipoles. So HCl has a fairly big dipole because chlorine's quite electronegative. HI has a much smaller dipole because iodine is not nearly as electronegative as chlorine is. This would be for the permanent dipole. Which one has a higher boiling point? Based on dipole, I would say HCl has a higher boiling point, right? Based on dipole, because the dipole-dipole interaction or attraction is going to be much stronger. And so based on boiling point, actually, I see something else. Which one has a higher boiling point? HI. Now, why would HI have a higher boiling point? It's got a smaller dipole. It's the size. Dispersion went out. For large molecules, dispersion can be quite significant. And so HI, it's not the dipole-dipole interaction, it's the dispersion. Now, how does dispersion work in something like this? Well, dispersion works in the same way. What happens is the electron cloud's polarizable, so this is its time average. But in one instant of time, if all the electrons in iodine migrate to this side of the iodine molecule, HI molecule, then we'll set up a very large instantaneous dipole. Whereas, you know, the largest instantaneous dipole we could set up with HCl isn't going to be as big because it's not nearly as polarizable. And so what happens is the electron cloud fluctuates. I mean, we could get smaller. You know, if electrons migrate towards hydrogen, this gets smaller, this gets bigger. And so smaller and bigger. Whereas over here at HCl, that range is much tighter, much smaller. And so the sheer magnitude of the dispersion force is going to be quite a bit less. All right, nonetheless, when we compare it for small molecules, you can see. And even for larger molecules like tin is much bigger, but ammonia still has stronger boiling point. HF to H2O. But as this increases in size, eventually these will dominate, unless there are a lot of hydrogen bonds. Actually, ammonia, HF, and H2O is what we call hydrogen bonding. Hydrogen bonding is quite significant. Here you can see how the HFs like to line up for hydrogen bonding. It tries to maximize that hydrogen bonding interaction. And it maximizes this, although this electrostatic potential map is hard to read. So let's draw a little electrostatic potential map. HCl does not hydrogen bond because chlorine isn't quite electronegative enough. You know, if I look at H consists of a proton. So let's take a look at the electron cloud. So there's some proton there. When Cl tries to pull the electron cloud away from hydrogen, and it's pretty successful. It can make a pretty polar bond. This an electron cloud could be distorted. Anyway. But if we were to bond H to a oxygen, let's say, and so H, there's a proton there, an electron, shared in here. Oxygen is quite a bit more electronegative, and so it strips more electron density away from hydrogen. And what results for hydrogen is what we call a partially exposed proton. Partially exposed. Partially exposed means unshielded. You know, normally you have the electron cloud shielding it. This is partially exposed, unshielded proton. And so that means we generate a very large delta plus here on the hydrogen. Whereas over here, this is shielded steel. You know, and so the delta plus we generate isn't nearly as big. And so this is approaching full charge. That makes it more significant. It's hard to see it in this electrostatic map. It makes for a very strong attraction. And so you have this very large delta plus here. This is going to be attracted to any negative regions here. This very large delta plus is a result of hydrogen being bonded to oxygen, or hydrogen being bonded to nitrogen, or hydrogen being bonded to fluorine. Fluorine, oxygen, and nitrogen are the three most electronegative elements on the periodic table. And so here's the hydrogen bonding interaction in water. Well, you know, to break this hydrogen bonding interaction takes about 25 kilojoules per mole. 25 kilojoules per mole, is that very much energy or not much? It's not much energy. I mean, if you think about a bond, you know, the weakest covalent bond is roughly what? 100 kilojoules per mole? And so even though they call it a hydrogen bond, technically it's not a bond. You know, you would expect a bond to be stronger. Hydrogen bonding is just an intermolecular attraction. And so in one sense, they're very weak. You know, it's not like a bond. In another sense, hydrogen bonds are the strongest of these weak forces.
How do you share the electron in H, the O, both O's? Like, which one takes more on the cloud?
Oh, these O's?
Yeah, these O's, like they're next.
Well, how do they share? You know, that's an interesting question because there's something called proton exchange, where this collides in here and plucks the proton off, leaving the electron cloud here. And so how do they share it? They don't really share it. I mean, in one sense, just this is bonded. This is going to be an sp3 sigma bond here. And all we're seeing is an electrical attraction between these two, delta minus and delta plus, but the electron cloud's staying on the oxygen. I don't know why he didn't write the lone pairs in here. Organic chemists are notorious for leaving off lone pairs. This is not an organic chemistry class. But the proton, you know, in one sense you could think of it as being evenly shared, because this hydrogen or proton can break off this water and attach to this one, and likewise things can happen. But if you look at the gap here, you know, the gap is indicating there's no sharing. Do you see that? This gap here indicates that they're not really sharing. It's just an attraction between these two unusually large dipoles. Now, water also has dispersion, you know, and so as electron density is further polarized, it can make this bigger or smaller, depending on where the electrons are at in one instant of time. Is water very polarizable? What would you say? Compared to something like xenon. Xenon would be highly polarizable. What about water? No. Water's not that polarizable. It doesn't have all that many electrons. These hydrogen bonding interactions you can see here. Quite a few hydrogen bonding interactions per molecule. It helps stabilize things. In the solid, the molecules arrange in order to maximize the hydrogen bonding interactions here. Let's see. When that happens, you get a very open structure, an open network of water molecules frozen in the solid state. And so solid water isn't very dense. There's a lot of what we call empty space or void space in here. This crystal. In the liquid, the water molecules can pack together a lot more tightly. So liquid water, because of the random nature of liquids, they don't have to orient like this in this very open framework structure. And so liquids are a lot more dense than ice. Ice floats on water. Sometimes these hydrogen bonding interactions are quite strong. Especially, look, we get two hydrogen bonding interactions here. Here we have an OH, here we have an OH. This is going to be attracted to delta minus here, minus here. This is acetic acid. And this is called a dimer. A dimer, just di means two, and mer means these monomers. Monomers, we have monomers, dimers, polymers, trimers, depending on how many of these units you put together. Well, dimerization like this is something we have to worry about for something like acetic acid. You know, acetic acid loves to orient itself like this and then stick. It costs energy to break both of those. And if you break one of them, the other one's still usually attached. You have to break both of them kind of simultaneously so they separate. And so these dimers are quite stable. And the dimers will change the way acetic acid behaves, like in solution, other things, because, you know, these two molecules are now stuck together. They aren't separate, independent molecules. So it's dimerization. Effectively cuts the concentration in half, what you think is the concentration, because now everything's paired. It's dimerization. The extent of hydrogen bonding can have a huge impact on the boiling point. And so I said size matters, but you know, if we go bigger and have more hydrogen bonds or hydrogen bonding interactions, then hydrogen bonding interactions can be hugely significant. So if we look at ethanol, ethanol has one OH out here. Ethylene glycol, two OHs. So ethylene glycol is going to have a much higher boiling point. And the highest boiling point of this series would be glycerol. Glycerol has three OHs. And so it can set up a lot of hydrogen bonding interactions with the surrounding molecules here, glycerol molecules. So glycerol is like a heavy syrup. You know, its boiling point is quite high. What these numbers are showing here is the viscosity. It's the symbol for viscosity. And high viscosity like this, 1490 CP, tells us this is like maple syrup. A low viscosity like this says this flows more than water. Viscosity is this resistance to flow. We'll talk about it in a minute. If we look at the electrostatic potential maps, this is an interesting hydrogen bond here. This hydrogen bond occurs within the molecule. And so this is called an intramolecular hydrogen bond. Intramolecular because it's within the same. And so this OH is kind of stuck here. you know, you expect free rotation of the OH, so the OH should be swinging and rotating around like this. But what happens is, because of this hydrogen bonding interaction, it kind of gets stuck here. And so to rotate this would cost you energy to break that hydrogen bonding interaction there in order to rotate it, so it's kind of stuck. This one, there's no such intramolecular hydrogen bond. Here, this would be intermolecular hydrogen bonding. And if you look at these two structures, the two structures are kind of well matched, because here we have a hydrogen bonding interaction here, another, oh actually, is this hydrogen bonding? We got. Yeah, I gotta look at it again. This might not be. This middle one looks like a dipole interaction. And so we have a mix of hydrogen bonding and dipole interactions here.
Why dipole?
Dipole because we need the hydrogen bonded to a oxygen, nitrogen, or fluorine. When I look at this one, it doesn't look like it. It's here.
You saying both?
I gotta figure out what that is. That's nitrogen. If that's nitrogen, we have nitrogen-hydrogen bond. Nitrogen-hydrogen bond here. This could be nitrogen. Yeah, I think this is a nitrogen-hydrogen bond here. So it would be 3 hydrogen bonding interactions.
Costs more energy, the first one, the third one.
To break?
Yeah.
This one, we're looking at the attraction within the molecule. So this is going to cost some energy to break this attraction here, but not huge. Yeah. This one for sure is going to cost more energy to break overall, because we got to break 3 hydrogen bonding interactions.
What if it was 1-to-1? What if it was 1-to-1 ratio?
1-to-1, then you mean one? That's what this previous slide was trying to show. Here, if you have 2 ethanol stuck to each other, then you just have 1-to-1. But if you have 2 glycerols, 2 glycerols means a 3-to-3 interaction. The 3-to-3 interaction is going to be kind of strong. It's going to be hard to break. And so it'll be hard to break these molecules apart.
But is there a difference between if it's intermolecular or intramolecular?
Intramolecular is not going to have any impact, really. The boiling point. You know, here we're going to have hydrogen bonding with another molecule. So here we could have some kind of hydrogen bonding interaction here. But if you look at it, the rest of the molecule isn't really properly lined up. And so we're just going to have 1 hydrogen bond right here and nothing here. Okay? And so to break these 2 molecules apart is going to take significantly less energy than to break these 2 molecules apart. Oftentimes when we're talking about boiling point, we aren't looking at 2 different molecules. These are 2 different molecules. We're looking at breaking apart 2 of the same molecule. Now, this is a carboxylic acid here group, and so this can dimerize also. You know, if we had another one of these and just flipped it upside down, then they can link up. Do you see that? We'll get the hydrogen bonding interaction there. However, that's still not going to be as strong as this. You know, everything's perfectly aligned here. Everything's perfectly aligned here because this is the guanine on the left, cytosine on the right, and DNA. DNA consists of 2 molecules, right? The double helix, and the 2 molecules are these super long chains, amino acids. And what holds the 2 molecules, these 2 long chains together in this helical structure, are the hydrogen bonds. Actually, I don't have DNA here. It's interesting because with computer modeling, you can turn off the hydrogen bond with a click of a button. You turn off the hydrogen bonds, DNA falls apart. You turn them back on again, it doesn't quite rearrange the same way it was before, but the hydrogen bonding interaction is very important.
When you're talking about hydrogen bonding, like it actually the electricity attraction,
Electrical attraction. All these are electrical attraction.
No real bond.
Hmm?
Not a real bond.
Not a real bond. No orbital overlap, no MOs, only electrical attraction. The reason they call it a bond is because it's fairly strong. Like these dimers are hard to break. So in that sense, it is kind of like they're bonded together. These two acetic acid molecules are bonded together. But from a bonding perspective, let's say it's 25 kilojoules per. That's only 50 kilojoules. 50 kilojoules is still not much energy. In DNA, you got a lot of these. Let's see. Now, there are other types of interactions. All these are electrical in nature, and so I didn't put those on here, unfortunately. But the other interactions that they talk about would be things like ion dipole. Like if you have an ion, like lithium ion in water. Lithium ion in water, is there any attraction between lithium ions and water? It turns out there are. The attractive force between lithium ions and water is an ion dipole because lithium is positive. Water is partially negative. And so ion dipoles can be quite strong. So if you got lithium here, the water molecules will want to orient with the delta minus pointed towards the ion. Now these are expected to be stronger than dipole-dipole. These are expected to be stronger than hydrogen bonding. Why? Because lithium ions have a full positive charge, not a partial positive charge. And so ion dipole is going to be stronger than, let's say, hydrogen bonding. But it also depends on, the size of the ion. So, for example, lithium ion you'd expect to have a strong interaction with water, whereas potassium ion would have a much weaker interaction with water because, even though potassium ion and lithium ion are the same charge, their charge density is quite a bit different. Lithium ions are a lot smaller, potassium ions are a lot bigger, and so the ion dipole attraction between water and potassium ion is going to be a lot weaker. Right? I talked briefly about the stability of the conjugate base. The stability of the conjugate base depends on charge, delocalization, and the stabilization of the conjugate base in water. I called that the hydration or the solvation. We'll talk briefly about that in chapter 13. So, strong interaction here, way stronger than hydrogen bonding for sure. Weaker interaction.
Is stronger than hydrogen bonding?
What? Yeah. Like, say, for example, if you try to dissolve lithium ion in pentane, what kind of attraction would there be here? This would be ion instantaneous induced. In other words, ion London force. Is this attraction going to be all that strong? No. This will be much stronger. We got the positive being attracted to the negative. Positive being attracted to the negative. Positive being attracted to an instantaneous, fleeting, short-lived negative.
Even in potassium is stronger than H bonded.
Oh, potassium now, that gets tricky. That gets very tricky to compare because, H plus is fairly small in size. And so negative species can come quite close to it. And so this could be this could end up being stronger than this because this ion is quite big, so the positive charge distributed over this ion, it's not going to have much positive charge density to it. And so those types of comparisons we like to avoid because it gets too complicated. If we need to do something more complicated, you know, this is why they say when we compare these forces, you compare them for small molecules. For small molecules is easy because hydrogen bonding wins out, right? But for large molecules, what typically wins? Dispersion. Now, if you have a combination of dispersion and hydrogen bonding, then that's going to be significant, like in DNA. You know, what's the melting point of DNA? What's the boiling point of DNA? I don't think you want to boil DNA. I don't think it boils very easily because, but it does melt. Do you know DNA melts? DNA melts. What happens when you melt it? You break these hydrogen bonding interactions. It's still, I mean, you partially break them. You know, they're still there. They just not holding it rigid. It's like water. When you melt ice, you partially break these. You know, the hydrogen bonding interactions are there. They just aren't maximized like they once were. In order to boil this, now you've got to completely break the IMF. In order to vaporize the liquid into the gaseous state, it's got to be completely free. So those are a review of some of the intermolecular forces, attraction. These are all familiar, pretty much. All right, let's take a look at some properties of liquids. Cohesive forces, or intermolecular forces between like molecules. Adhesive forces are intermolecular forces between unlike molecules. They don't even have to be molecules, these surfaces. There's surface tension. Surface tension is the energy or work required to increase the surface area of a liquid. There's viscosity, which is the resistance to flow. There's delta H of vaporization, which isn't on here, we'll talk about, and vapor pressure, which isn't on here. Here's an example of surface tension. Here's this needle. The needle should sink because the metal is more dense than water, but it doesn't sink. If you're very careful not to break the surface, right? It won't sink. The reason it won't sink is because, you know, you have a fight between gravitational potential energy versus surface energy. When we look at the surface molecules are higher in energy. They're higher in energy because they aren't as stabilized. If you look at this as 1, 2, 3, 4 IMFs holding that surface molecule down. Whereas if we look at an interior molecule, you know, 1, 2, 3, 4, 5, there are more intermolecular forces stabilizing that molecule and holding it in as a liquid. And so what we say is that surface molecules have higher energy, interior molecules have lower energy. And so if we're increasing the surface area of a liquid, we're actually going from lower energy to higher energy. That's endothermic. It's going to cost you energy. How much energy does it cost? Well, that's been measured. And so you can float small objects like this, but larger objects are going to sink right down. We aren't going to worry about it, but all we're going to say is that the stronger the IMFs, the higher the surface tension. The stronger the IMFs, the higher the surface tension. It means the surface is going to be harder to break. You could do this with water. You know, if we had a cup of mercury here, you know lead floats on mercury? Well, that could be a density effect, not a surface tension effect. All All right, let's take a look at cohesive versus adhesive forces. This is called wetting. Do you know what this is called? Beating. Wetting, beating. So what's the difference? Well, both of this is water. And so water wets the left side of this slide, but beads on the right side. And it has to do with the surface. Over here, this is clean glass. Over here, this is dirty glass or wax glass. And so if we put a coating of wax on here, water tends to bead. And so what's happening here is this. When we have wetting of the surface, that means the water likes the glass. It's attracted to the glass. So water wants to maximize its surface contact with the glass. Over here, water doesn't like the surface, so it wants to minimize its surface contact with the wax. And so here, what we'll say is that the adhesive forces, adhesive would be the forces between water and glass, are stronger than the cohesive forces. Cohesive forces would be water and water. And so when we have wetting, the adhesive forces are stronger than the cohesive forces. When we have beating, the opposite is true. When we have beating, the adhesive forces are weaker than the cohesive forces. That is, the water-water attractions are stronger than the water wax. It's probably wax. This is taken to an extreme. This is a ball of liquid mercury. Now, this is weird because gravity should force this to its minimum gravitational potential energy. Its minimum gravitational potential energy is force it down into a thin, shallow pool of liquid mercury, at minimum height. But it doesn't. This ball of liquid mercury stays in the ball like this. One, to maximize cohesive forces, right? And so the cohesion between mercury atoms is quite strong. Much stronger than the adhesion. It doesn't want to stick to the glass. In fact, look at it. It's trying to minimize its surface contact with glass. It hates glass. And so, in other words, adhesive forces are incredibly weak. The cohesive forces are strong. So here we can see an extreme case of that. It's hard to build a bead this big. Smaller beads are easy, but this is a pretty impressive sized bead. And so mercury does not like glass. We can see that here in the meniscus. Does mercury like glass? No, it doesn't like glass. Mercury does not like glass, so it tries to minimize its contact with the glass. In other words, the cohesive forces, mercury likes mercury. Mercury wants to stay with mercury. Cohesive forces are stronger than the adhesive forces. Over here, water and glass. Water loves glass. Water loves glass, and water tries to climb up the surface of the glass to maximize its surface contact with glass, except one thing holds it back. Do you know what holds it back? Gravity. So eventually it can only climb so high because gravitational potential energy would be too much to overcome. Unless you have something like this, a very small tube, because gravitational potential energy depends on mgh, how many grams of water you got. And so if you have a thin tube like this, thin tubes are called capillaries. The water can climb quite high up a capillary because we aren't lifting that much mass of water. And the adhesive forces are quite strong. So here is where the adhesive forces are balanced with gravitational potential. Now, if there was zero gravity, this would just climb all the way to maximize its contact with the glass. It's capillary action. Viscosity is just the liquid's resistance to flow. So a lot of you have already experienced, like maple syrup. Maple syrup has a very high viscosity. Maple syrup consists of sugar. Sugar has lots of hydrogen bonding interactions in it. And so those hydrogen bonding interactions means that it's difficult to move those sugar molecules around. It's viscosity. Another thing related to intermolecular forces is the enthalpy of vaporization, or the heat of vaporization, delta H of vaporization, which is the opposite of condensation. Now here's some enthalpies of vaporization at 298 Kelvin. If we look at diethyl ether, this is bent around oxygen. This has a permanent dipole, so there's dipole and dispersion. 29.1 kilojoules to vaporize a mole of it. Methyl alcohol has hydrogen bonding interactions. Hydrogen bonding interactions can be stronger than dipole. It's 38. Ethyl alcohol not only has hydrogen bonding, but it has more electrons. And so it's greater dispersion than methyl alcohol. It's 42.6. In fact, there are a lot of alcohols that are actually solid. You know, if you keep adding carbons to this chain, you get to like pentanol, hexanol. They become, because of the dispersion. Water has a very high delta H of vaporization. There's 2 hydrogen bonding interactions per molecule. Okay, vapor pressure of liquid is another one. You know, if it doesn't cost much energy, then molecules can vaporize quite easily. If it doesn't cause much energy, then the boiling point should be small. You know, you could just replace this with boiling point. You know, the highest boiling point will be water, and these would be lower boiling points. And boiling point and delta H of vaporization go hand in hand. Well, this is what we have going on with vapor pressure of liquids here. If we put a liquid into an empty container, let's say a vacuum, what happens is not all the liquid molecules have the same kinetic energy. We have a distribution of kinetic energy, so some of the molecules are going to have enough energy to vaporize off the surface. We call that evaporation. Evaporation will continue, and we'll get more and more molecules into the gaseous state. But as we get more molecules into the gaseous state, then this becomes probable. The molecule comes back and strikes the surface of the liquid. The molecule that comes back and strikes the surface can stick because of the intermolecular attractions. And so the blue process is called condensation. Right here we see a net evaporation or vaporization. The vaporization rate is greater than the condensation rate. And so this is what we call unsaturated. However, once the concentration of gas molecules builds up so that the condensation rate is equal to the evaporation rate, then we've reached a state of dynamic equilibrium. Equilibrium because the vapor pressure is not going to change. And so the vapor pressure is pretty much constant. Vapor pressure is going to be the pressure exerted by all these gas molecules on the inside wall of the container. But it's a dynamic equilibrium because this process, evaporation and condensation, don't stop. And so we have something called chemical exchange, where the molecules are being exchanged continuously between gaseous state and liquid state. If you were trapped inside here, and this were water, this would be called 100% relative humidity. You know, maybe this is about 50% relative humidity. It looks like we got half, right? This would be close to 0%. And so once we hit 100% relative humidity, it can't get more humid than this, right? Because if you blast more molecules in here, the condensation rate will match it or exceed it, and then things will balance out. What will change the relative humidity is temperature. You know, at colder temperatures, can the humidity be as high? No, because at colder temperatures, the evaporation rate is lower. If the vaporization rate is lower, then it doesn't take as much to saturate this and build up the condensation rate that's equal and opposite. At higher temperatures, what happens? At higher temperatures, the vaporization rate is even higher. the vaporization rate is even higher, then we have to match it with a condensation rate that's equally as high. And so that's going to saturate this more. And so higher temperatures, it becomes more saturated. I mean, there's more gaseous molecules. At lower temperature, there's fewer, but we call it saturated at all temperatures nonetheless. So this is 100% relative humidity. 100% relative humidity varies depending on the temperature.
Can we survive at 100% humidity?
Yes. Not very well.
Is it the water cools down as price?
What's that?
The water cools down, yeah, as
It evaporates?
Yeah.
But the thing is, water is going to cool down as it evaporates, but it's going to warm up as it condenses. And so, you know, delta H of vaporization is equal and opposite of delta H of condensation. And so the amount of energy that you cool down will be exactly equal to the amount of energy that you warm up, and with no net temperature change.
well, you said it keeps going in the same circle, yeah.
Yeah.
Where do you get the energy, right? There's no energy loss.
The energy just comes from kinetic energy, the temperature. You know, if we look at the Maxwell-Boltzmann distribution, you know, there's going to be a certain fraction of molecules with sufficient energy to vaporize off the surface. And so it just normally occurs, the vaporization. Right? Because some of those have enough energy to escape the intermolecular forces.
But eventually they will stop, yeah, like there's nothing happening.
Eventually they will stop? You mean they'll lose energy?
Yeah.
It's just going to go like that, perpetually. Do you think this is a violation of the second?
Yeah.
Do you think this would be a violation of conservation of energy because of that? Where's that energy coming from? But it's not. I mean, the energy's there because of the temperature. Temperature being kinetic energy, it's always there. So there was some energy there. So the energy is what's powering it. If this were at 0 Kelvin, then what would happen? At 0 Kelvin, freeze, basically. Freeze, and then you wouldn't have anything happening. And so we're adding the temperature in there. It's just that.
So it's getting the energy from the surrounding layer.
Yeah, it's getting energy from the surroundings, and then it actually, the system already possesses energy. So it's kind of tricky, but you don't have to worry about it. You can think about it. Well, looking at these here, this is just how to measure vapor pressure. You can inject the liquid here and see how the pressure changes. So originally we have this, inside. The weight of the liquid is equal to the weight of the atmosphere. And we add this in, so we not only got the weight of the liquid, but we got the pressure of the gas in here. The weight of 2 different liquids. And so we can measure the vapor pressure. These diagrams you don't worry about at all. All you see is something like this, that the vapor pressure depends on the temperature. And so the hotter this is, the higher the vapor pressure. And we can measure it and put it into a table. This table might look familiar. This table is the vapor pressure of water at various temperatures table. And we had to use this. Do you remember we had to use this for like some kind of interpolation? You guys remember that? And so we had something like 23 degrees C. What would the vapor pressure be at 23 degrees C? Well, it's 21.1, but what if we're at 23.3? There's no entry at 23.3, so what is the vapor pressure? You guys remember doing linear interpolation? This is linear interpolation based on experimental data here, like this. But is it linear? Is it really linear? Let's plot this data out. If we plot this data out, we get this black line here. This is water. And we'll see it's nonlinear. That is, as the temperature increases, the vapor pressure increases exponentially. And so that's kind of weird, because in a normal gas, what happens? You know, in a normal gas, as the temperature increases, the pressure increases linearly according to the ideal gas law. And so if we're looking at normal gas, we expect a linear increase in pressure with temperature. But when we're looking at vapor pressure is the pressure exerted by the gas molecules. The vapor pressure of the gas increases exponentially as the temperature increases. What causes it to increase exponentially? What causes the vapor pressure to display this nonlinear behavior is this. As we increase the temperature, yes, the gas is going to get more kinetic energy. The gas gets more kinetic energy and the collisions with the wall become more severe and the pressure goes up. More severe, more frequent. But as we're increasing the temperature of the gas, we're also increasing the temperature of the liquid. As you increase the temperature of the liquid, what's going to happen? You're going to vaporize a lot more liquid molecules into the gaseous phase, which means that not only do we have a gas here, but the amount of gas is growing exponentially. And so that's what causes the exponential increase. It's the amount of gas molecules being vaporized into the gaseous state is increasing exponentially. And so this is why the vapor pressure curve doesn't look like a typical pressure curve. You know, a typical pressure curve with an ideal gas is linear. And so the pressure shoots up like this. So is it linear interpolation okay? Well, linear interpolation is okay if the intervals are very small, but if the interval that you're interpolating is very large, let's say from here to here, then linear interpolation is not good. You know, because if you linear interpolate between, let's say, these two temperatures here, then you'll come up with some kind of value out here, which isn't good. And so linear interpolation is good if you have a lot of data. And so you can draw straight line segments between all these data and kind of mimic this curve. What's better than linear interpolation? Well, just going off the curve here. You know, if we were at 22.8 or 23.4, we just measure 23.4 here, go out to the curve, and then measure, here, temperature. Temperature here, go up to the curve, and then measure out its vapor pressure here. And so we could graph this data out and then just analyze it like this. You know? There's one temperature that's quite significant for water, and that's 100 degrees C. Because at 100 degrees C, the vapor pressure of water is 760 millimeters of mercury. 760 millimeters of mercury, you should know that as normal atmospheric pressure. Normal atmospheric pressure gives us the normal boiling point. And so when the vapor pressure of the liquid matches normal atmospheric pressure, the liquid will start to boil. Boil is just vaporized spontaneously. And so that is, you have atmospheric pressure pushing down, you got the vapor pressure pushing up, and they're equal. Opposite, yeah. And so what we see here is the blue. This one has a lower boiling point. You know, it's 100. This boiling point's around 80. The red, this one has the lowest boiling point out of all these. The boiling point is around 30. D has a higher boiling point than water, around here, and E has the highest boiling point, somehow out here. The boiling point is going to be related to the intermolecular force. So these two have weaker intermolecular forces. These two have stronger intermolecular forces of attraction than water. This is the normal boiling point, but we can predict. Like, for example, what is the pressure in Denver? You know what the atmospheric pressure in Denver is, Colorado? What is it?
It's like 72 or
752. So it's below 760. So we could figure out water in Denver, Colorado would boil at a lower temperature. Because boiling, we just have to match atmospheric pressure. That's it. Whereas water, you know, in a pressure cooker would boil at a much higher temperature, because in a pressure cooker we have higher pressures that we have to overcome, and we'd have a higher boiling point. Okay, this, if we plot this on semi-log paper, we could get linear. Linear is easier to fit mathematically, but we're going to skip this because these equations aren't so easy to use. And we're going to talk about one equation that we can use. We want to fit this mathematically. And to fit this mathematically, rather than doing linear interpolation or graphical analysis of this, we could use this equation. And this equation has been modified to make it easier to use. That is, natural log of P2 over P1 is equal to minus delta H of vaporization over R, 1 over T2 minus 1 over T1. What this allows us to do is it allows us to calculate the vapor pressure at any temperature. And so let's say you wanted the vapor pressure of 23.5 degrees. We could use this equation to do that. This is called the Clausius-Clapeyron equation. So normally we'd need a delta H of vaporization here. And so for example, water, H2O liquid, has a delta H of vaporization of minus 44.0 kilojoules per mole. And it has a vapor pressure, P1, of 760 millimeters of mercury at a T1 equal 373 Kelvin. And so we know this is the normal boiling point. We know that. And so we could calculate the temperature for any vapor pressure. And so if Denver is at 748 millimeters of mercury for a particular day, then what is the boiling point of that water for that particular day? Or if you go and climb Everest and the vapor and the atmospheric pressure were like 400 millimeters of mercury, where would water boil? Water would boil at an extremely low temperature. And so the Clausius-Clapeyron equation allows us to not have to deal with a table like this. And so we can eliminate this entire table. We don't have to deal with graphs like this. We just plug it into an equation like that. This also allows us to determine delta H's as well, if you don't have that data already. All right, I'm out of time, so let's stop here. If there are questions, we can cover those. Okay, are there questions?
You don't need to email the Excel.
No, don't email it.
Same for the other one. Do you want these?
Yeah, for experiment 2, just take a look at the equations. You could turn it in after the final if you could just. It probably won't even take very long to finish that up.